Good day, this is laboratory experiment number 4, Newton's method using MatLab. This activity will allow the student to implement Newton's method using MATLAB, Freemat, Mathematica, or similar software. Our objective is by the end of this activity, we are expected to be able to construct a function using MATLAB, demonstrate your understanding in Newton's method, understand and implement Newton's method to find the root of a function using software. Materials needed is MATLAB, Freemat, Mathematica, or similar software. Okay, procedure. The pseudocode can be found in Numerical Mathematics and Computing, 6th edition, Ward Sheeny, David Kincaid, page 92. Demonstrate Newton's method using MATLAB. Calculate the roots of our user. Define function with the following specification. Function tag Newton method. Arguments y tag f x 0 TOL and max, where f is defined as the function and xo is the initial value of x. TOL is the tolerance and max is the maximum number of iterations. Next procedure is to put all the codes on a *.m script or suite of scripts that is loadable in MATLAB. The MATLAB function should accept the user's defined function as an input argument and produce a variable containing the answer. Okay, so we are now on our experiment, and we want to write a program for implementing Newton's method where we avoid the division by 0, allow maximum number of iterations, avoid extra evaluation to the function x. Okay, so I've been trying to make the program from our reference work, but it seems that my MATLAB here couldn't read the pseudocode, so I made one myself, and after plenty of hours of tinkering and asking questions in the forum, I came up with this. So we would try and solve a function x squared minus 9 is equal to 0. Okay, and we've entered the function here with a call sign. We've entered the number of iterations or errors and iterations. Okay, and okay, we just need to run the program now, and handling of the potential division by 0 is done by a try-catch construction, which works as follows. First, MATLAB tries to execute the code in the try block, but if something goes wrong, then the catch block is executed instead, and execution is terminated by exit here. The division by 0 will always be detected and the program will be stopped. The main purpose of our way of treating the division by 0 is to give the user a more informative error message and stop the program in a gentler way. Calling exit with an argument different from 0 signifies that the program stopped because of an error. it is a good habit to supply the value of 1 because tools in the operating system can be used by other programs to detect that our program failed. To prevent an infinite loop because of divergent iterations, we introduce the integer variable iteration counter here. We can easily extend the condition in the while such that no more iteration take place when the number of iteration reaches to 100. We'll easily let this limit be an argument to the function rather than a fixed constant. The Newton function returns the approximate solution and the number of iteration. The latter is equal to -1 if the convergence criterion of the absolute value of f of x is less than epsilon was not reached within the maximum number of iteration. In calling the code, we print out the solution and the number of function calls. The main cause of a method of solving f of x equals 0 equations is usually the evaluation of f of x and f prime of x. So the total number of calls to this function is an interesting measure of the computational work. Note that in the function Newton here is an initial call to f of x, and then one call to f and the one to f prime in each iteration. Okay, running on Newton's method, we get the following print out on the screen. Okay, we now run our program. Okay, the number of function of calls is 25, and the solution on our initial problem of x squared minus 9 is equal to 0. So our answer to our solution is 3. So I hope you learned something, and this concludes our experiment number 4. Thank you.